This topic is the start of a piece on enzyme catalysis. So, our goal today is to talk in general about different ways in which enzymes can catalyze reactions. And then we're going to give an example that talks about really acid base catalysis in some detail. And then the next topic that we're going to do in our next class will have a lot of these components in it. So, how do enzymes catalyze reactions? Well, there's 6 basic categories, ways in which enzymes can catalyze reactions. They can provide acids or bases. They can make a covalent bond with their substrate that affects the energy of the transition state. Sometimes enzymes use metals such as zinc or magnesium or iron in order to provide some functionality that helps the reaction go forward. And then there's electrostatic interactions, proximity orientation effects, preferential binding of transition state complexes. We'll go through each of these and just explain them basically. And keep in mind that enzymes don't have to just choose one of these things. They can use all of these different types of mechanisms of catalysis in order to speed up a reaction. So the easiest one to think about really is acid-base catalysis. We use acids and bases all the time in organic chemistry as catalysts to promote a reaction, making it go faster. And we already know that a lot of amino acids have acid or basic functional groups. One of the really common amino acids that's seen in acid-base catalysis in biochemistry is histidine. Right, here's histidine over here. It has a pKa of right around 6, which is kind of close to the pH that occurs in a cell. And therefore, histidine can act as an acid and as a base in a reaction. This proton here can be donated, acting as an acid. This lone pair on this nitrogen can act as a Lewis base to accept a proton. And what we know about catalysts anyway is that in order for an enzyme to do acid-base catalysis, really it's going to have to do both of those things. An enzyme can't just act as an acid, donate a proton to a substrate, and producing a product from that, because that changes the enzyme. It's donated that proton. And we know that all catalysts really don't change in the course of the reaction. So in order for an enzyme to be a true catalyst and undergo acid-base catalysis, if it acts as an acid, let's say this histidine donates this proton to the substrate, sometime later in the reaction, this nitrogen has to accept a proton from something else to restore its original state so that it can act as a catalyst to the next substrate. And so histidine is often seen as acting as an acid and a base during the course of a reaction. So let's look at an example of an enzyme called RNase that uses histidines like crazy as acid-base catalysts in order to cleave RNA. So here's a diagram of the mechanism of the RNase reaction, and let's orient ourselves to it. Okay. First things first, let's see, this brown sort of semicircle here represents the active site of the enzyme, right? So the rest of the RNase protein is presumably on the other side of this brown barrier, but this little pocket that's formed by the brown semicircle is the active site. In that active site, we can see 2 histidines that are part of the RNase protein, histidine 12 at the 12th position and histidine 119 at the 119th position. Now, this is a good example of how the primary structure of RNase has a histidine at 12 and one very far away in the primary structure at 119. However, in the 3-dimensional shape of this protein, this globular protein, in physical space, 12 and 119 are actually really close together and are interacting with each other. So, in the active site of RNase, we have these 2 very important histidines. We also bind to our substrate. So in black here is the RNA molecule that we're familiar with because we know about nucleic acid structure. We can see our ribose sugar, are phosphodiester linkage between different nucleotides of our RNA, and each of them has a base associated with it. Now, RNase is a protein that cleaves single-stranded RNA, and we can look sort of through this mechanism, and we can see it's going to cleave it right at this phosphodiester bond. Okay. So how does this work? Well, let's go through this mechanism pretty quickly on this slide, just by looking at the arrows, and then we'll look at a video that shows it in a little more detail. So, what happens? Well, first, we can think of histidine 12 as acting as a base. Right? This nitrogen is acting as a Lewis base with its lone pair and removing this hydrogen from the 2' position of our ribose sugar. Now, what does that do? Well, these electrons then are associated with this oxygen, making it negatively charged, which makes it a really good nucleophile, right? When it was an OH, it's not a good nucleophile, but when we turn it into an O- by removing this hydrogen from the histidine 12, it becomes a really good nucleophile. And it attacks the phosphorus atom of the phosphodiester linkage. When it attacks this phosphate or the phosphorus atom, it creates a new bond between the phosphorus and this oxygen on the 2' position. That's too many bonds for this phosphorus to take. So we can think of the electrons here from the double bond coming out, coming back in to reform that phosphorus-oxygen double bond, and then this phosphorus-oxygen double bond breaking. Now, when this bond breaks, it's going to, cleave the RNA, which is the whole point of the enzyme. But it also generates a leaving group that's not a very good leaving group. This second part of the RNA molecule will leave when this bond is broken as an O-. Now, an O-, as you remember from organic, like a hydroxide or something like that, or a methoxide, is not a good leaving group. But we can make it into a better leaving group by protonating it. And that's where histidine 119 comes in. In order to break this bond and make this leave, we can generate a better leaving group by protonating this oxygen through the acidic action of histidine 119, donating this proton to the oxygen that's leaving. And here it is. We can see the second half of the RNA molecule has left, broken, and it's taken a hydrogen from histidine 119 to make it a good, stable leaving group. Okay. So let's go through this again. Histidine 12 acts as a base to generate a good nucleophile. That nucleophile attacks the phosphorus of the phosphodiester linkage, and this bond breaks. The leaving group leaves, made more stable by protonation from the acidic histidine 119. Now that's great. We have cleaved the RNA. It's in 2 pieces, but our enzyme is not in its original state. And so we've got to get that enzyme back to the original state. And so what happens is these histidines actually do the opposite of what they did in the first step. Histidine 119, which acted as an acid, is now going to act as a base, removing a proton from water. That generates a hydroxide group, which is a good nucleophile. That good nucleophile, just like the good nucleophile we made in step 1, is going to attack the phosphorus. We're going to break this phosphorus-oxygen bond. This would leave, again, as a negatively charged oxygen, which is a terrible leaving group. We'll make it into a good one by protonating it with histidine 12. What that does is it regenerates the original ionization state of these 2 histidines so that our enzyme can bind to the next substrate, and it gets rid of the rest of the RNA substrate as a leaving group. So these histidines do really kind of a pretty dance here, right? Histidine 12 acts as a base, generate a good nucleophile, while histidine 119 acts as an acid to generate a good leaving group. And then they switch roles. Histidine 119 now is acting as the base to generate a good nucleophile, while histidine 12 will act as an acid, getting rid of that proton that it accepted in the first step to generate a good leaving group. They're sort of tossing these protons back and forth like a baseball, in order to catalyze this reaction by generating good nucleophiles and good leaving groups. Now let's look at this, an animation of RNase. You can see it's a globular protein here. It's got some disulfide bonds. And just over on the right side, we can see this is probably where the active site is, where those two histidines are interacting with our substrate. We see there's a bunch of alpha helices in it, and here is a nice anti-parallel beta sheet, right in there. Now, let's look at the mechanism with an animation and see if we can get this straight in our head. Okay, so here's our two histidines in the active site. Here, the active site is shown as just this pocket in the middle. Histidine 12 is deprotonated. Histidine 119 is protonated at the beginning of the reaction. Okay, so here comes our substrate, our RNA molecule. Our histidine 12 generates a good negatively charged oxygen, good nucleophile, which attacks our phosphorus. This bond breaks and leaves as a good leaving group because it becomes protonated by histidine 119. Now, that screws up our enzyme, so we bring in water for the second half of the reaction, and the histidines switch their roles. Now histidine 119 is acting as a base to generate that good nucleophile, and histidine 12 is going to act as an acid, donating its proton to make a nice alcohol leaving group, and our RNA is cleaved.